Okay, so in yesterday's class, we looked at the concept of pH, why we have hydrogen ion concentration being expressed as pH, because the actual hydrogen ion concentration is only 0.00004 milliequivalents per liter. Okay, and then we also saw that the hydrogen ion concentration has to be tightly regulated. Any change in the hydrogen ion concentration is not good, because the cellular metabolism is going to be affected and also the brain activity is going to be affected. So we have some defense mechanisms, or we have some systems incorporated in our body, which are going to see that the hydrogen ion concentration in our body is not going to change much. Okay, so what are those defense systems? Those defense systems are the blood buffer systems, the role of the lungs, the second line of defense. First is the blood buffer systems, second is the lungs, and the third is the role of kidneys in maintenance of acid-base balance. To make any sense about the acid-base balance, you have to understand about an equation. What is that equation? Anybody can come online and tell me what is that equation? What is that equation? This group?
Henderson-Hasselbalch equation.
Yeah, you have an equation called as Henderson-Hasselbalch equation. And if you look at that equation, he says that pH is equal to pK plus log of bicarbonate divided by 0.03 into partial pressure of carbon dioxide. Okay, so this is the equation. This is the Henderson-Hasselbalch equation, which I've shown you yesterday, right? Now, the thing is, if you have you all written down the Henderson-Hasselbalch equation? Raise your hands.
Yes, sir.
Huh?
Yes, sir.
Under Rasarandi, if you're written, you can just raise your hand and tell me. Okay, so if you just look at that Henderson-Hasselbalch equation, you'll see that two things are ultimately going to determine the pH. One is the bicarbonate ion concentration. The other one is the partial pressure of carbon dioxide. The bicarbonate ion concentration is maintained by the kidneys, and the partial pressure of carbon dioxide is regulated by the lungs. So by interplay of these two organs, the pH is going to be determined. And pK for the system is 6.1. Ultimately, that equation can be rewritten as pH is equal to 6.1 plus log of bicarbonate divided by 0.03 into partial pressure of carbon dioxide. Why it is 0.03? Anybody?
Partial pressure of water.
Solubility of carbon dioxide.
Little slowly and loudly you tell me. Why it is 0.03? Anybody?
That is solubility of carbon dioxide.
That is what of carbon dioxide?
Solubility.
Solubility. Who is this? Ruhi, huh?
Yes, sir.
Can you explain it a little more?
So earlier it was the concentration that has to be written, but if we are writing in terms of partial pressure, then we have to multiply it by solubility to express in that form.
It is not exactly, you can say it as solubility. It's just like for every 1 millimeter of mercury of partial pressure of carbon dioxide, they have found out that 0.03 ml of carbon dioxide is found to be dissolved in the blood, the plasma. Okay, so for every 1 millimeter of mercury of carbon dioxide, around 0.03 ml of carbon dioxide is found. So like you told, it has to be concentration. So that is why the total partial pressure of carbon dioxide is multiplied by 0.03. Anyway, different books are giving different explanation. I think what you told is given in guidance. Okay, so 0.03 it is multiplied. Then we saw the role of the buffers, right? So buffers are the ones which come into play very quickly. But what you have to remember about the buffers is buffers don't give a long-lasting solution. Buffers will provide a temporary solution to any acid-base imbalance till the other two organs, that is the lungs and kidneys, can come into play. Okay. So what are the blood buffer systems? We saw yesterday that the buffer systems in the blood are bicarbonate system, and then you have the proteins which are there, both extracellular and mainly intracellular, mainly hemoglobin and other intracellular proteins. And then you have phosphate, which is a very important buffer system in the intracellular fluids, and more importantly in the tubular fluid. And these are the ones which come into play immediately. The next line of defense against any acid-base imbalances is the lungs will come into play. The lungs will adjust acid-base imbalance by controlling the carbon dioxide, partial pressure of carbon dioxide. So if there is an acidosis, the rate and depth of respiration will be increased, and that is going to cause the carbon dioxide to be blown off. Two people have raised their hands here. Any doubt in the first group? Any doubts? Can I continue? You can just raise your hand and tell me. I'll continue. Raise your hand. In this group, it's in the first. Okay. So the lungs will provide the thing by adjusting carbon dioxide. In case of acidosis, carbon dioxide will be blown off. In case of alkalosis, the carbon dioxide will be retained. Addition or removal of carbon dioxide means adding and removing hydrogen ions. That much concept you have to have it. The next organ, the kidneys, that is the one which will provide permanent solutions to any acid-base imbalances. Most often we see that when the kidneys are acting, they act little slow. They respond a little slow. Okay, but once they respond, whatever solutions they provide, they are long-lasting solutions. The same thing in blood pressure also. You have neural mechanisms, you have the intermediate acting mechanisms, and you have the long-lasting mechanisms, which is a kidney. So after all these mechanisms, kidneys will respond little slowly in blood pressure, but kidneys will provide more long-lasting solutions to blood pressure derangements. Same thing in acid-base balance also. First is the blood buffer systems, then you have the lungs coming into play, and then last you have the kidneys coming into play. But kidneys, just because last least but not the last but not the least, like that. Don't think it just because it is coming last, it is not important. It's the most important. They are the one. The kidneys are the ones which provide the long-lasting and permanent solutions to any acid-base imbalance. This is another concept that you have to have in your mind. How do the kidneys provide any solution to acid-base imbalances? So kidneys will provide solutions to acid-base imbalances by three mechanisms: by secreting hydrogen ions, by reabsorbing bicarbonate ions, and third one is by forming new bicarbonate ions. The combination of these three is done, and that will provide the solutions to acid-base balances. Say, for example, if there is acidosis, person is having acidosis due to whatever reason, kidneys have been stimulated. Kidneys will secrete hydrogen ions. They will reabsorb most of the filtered bicarbonate, and they will also start forming new bicarbonate so that this acidosis is correct. Okay. But if there is opposite situation, alkalosis, then reverse will happen. The kidneys will stop secreting hydrogen ions. They will not reabsorb the filtered bicarbonate, and they will not form new bicarbonate ions. So by this, they can adjust the alkalosis. In fact, they may also start excreting or secreting more of bicarbonate ions in the case of alkalosis. So by a modification of these three processes, whether it is acidosis or alkalosis, the kidneys are going to provide solutions to acid-base imbalance. And then we saw in yesterday's class that the way this is done is different in different parts of the nephrons. So you've taken down this diagram, say this one. So this is in the early part of the nephron, the proximal tubules, the way the hydrogen ion is secreted for sodium exchange, sodium hydrogen. You're able to hear me in this group? The second group, you're able to hear me? Some problem with the connection. Coronavirus is disturbing us. Huh? Will I continue?
Yes.
You can raise your hand, man. No need to talk. Can I continue? There was some problem in the second group. Shall I continue? Okay, so this is the mechanism in the proximal tubule. Point to be noted that you have a special type of transport protein, sodium hydrogen exchanger. And I also gave you this concept, is it not? That if you look at the tubular cell, the entire cell membrane, you can divide it into two parts. What are those two parts? Anybody can come online and tell me, unmute. What are the two parts of the? Okay, very good.
Luminal membrane, basolateral membrane.
Yeah, very good, very good. So you have the part of the cell membrane which is facing the tubular lumen. We will call it as the luminal membrane. And the remaining side parts and the one which is resting on the basement membrane, we will call it as basolateral membrane. The transport proteins which are present on the luminal membrane are different from the transport proteins which are present in the basolateral. You can see that here. So here in the luminal membrane, you have sodium hydrogen ion exchanger. It's a co-transport mechanism. Whereas in the basolateral membrane, you have the sodium potassium ATPase. Yeah. If you want, see, one thing I want to tell you all here, if you want to make any sense about the reabsorption and secretion in the kidneys, please read up transport across the cell. You have to read up transport across the cell, the various processes by which substances are transported across the cell. So you have the passive transport mechanisms, active transport mechanisms, the carrier proteins, the SIM port, antiport, and all that you have to look up. Otherwise, you will not be able to make any sense about the processes which are going on in the kidney. You know, internet unstable and must So this one we saw this diagram yesterday, and then one enzyme, very important enzyme is there, that is the carbonic anhydrase enzyme. Okay. Then we saw this happening in the distal tubule, where the intercalated cells will secrete hydrogen ions actively by the H plus ATPase, and along with H plus the chloride ions are going, and the different types of proteins which are there in the basolateral membrane. You have the anion exchanger, which exchanges chloride for bicarbonate. Then we looked at the importance of the buffers. Okay, so the buffer systems are very, very important. If the buffer systems were not there, and the kidneys would not have been such efficient organs in maintaining acid-base balance. The reason I made the statement is, if you look at the range of the pH in the urine, it is around 4 to 8, roughly, maybe 4.5 to 8. So you remember 4 to 8 is the range, pH range in the kidneys. Means kidneys cannot acidify urine below 4.5, and they can't secrete alkaline urine more than 8. This limit is there. Nature has put that limit. Okay. So I told you in yesterday's class that a person on a normal diet weighing around 70 kgs, he is going to be producing how much of non-volatile acids?
80 milliequivalent.
80 milliequivalents of non-volatile acids are there. Yeah. So 80 milliequivalents of non-volatile acids are there. This has to be excreted out. So as the kidney starts excreting this 80 milliequivalents of non-volatile acids, the lower limit would have been reached very quickly, and we would have needed around more than 2,000 liters of urine to be formed to remove that much of non-volatile acids. That situation is not arising because of the buffers. The buffers will not allow the pH to fall below 4 very quickly. And we have the phosphate buffer system and the ammonium ion buffer system. So this is the phosphate buffer system. And whenever you have the buffer systems buffering the hydrogen ions, you will see on the basolateral side that this side, see on this side, a new bicarbonate ion is being added. Very important mechanism for the maintenance of the acid. Then you have the ammonium ion. Okay, ammonium ion is produced by the metabolism of glutamine. Whenever glutamine is broken down, it is metabolized into 2 bicarbonate ions and 2 ammonium ions. Ammonium ions cannot cross the cell membrane on their own. There is a special transport protein in the proximal tubular cells that is going to pump out the ammonium ions, exchange ammonium ions for sodium. Okay, so because of the operation of this exchanger, ammonium ion is entering into the tubular fluid, and it may combine with the chloride ions to form ammonium chloride, and it can be there in the dissociated form. The ammonium ion and chloride can be present in the dissociated form. You all have taken down those diagrams yesterday? Raise your hand. I'll give you 2 more minutes quickly to take down those diagrams. So if you're not taken down this diagram, quickly draw it. Okay. Then let us move on to the next thing. So this shows the ammonium ion buffering system, right? So I told you that ammonium ion cannot cross the tubular membrane, cell membrane, whereas ammonia can easily cross the cell membrane. And this ammonia, which is there in the tubular cells, it enters into the lumen. From the cell, it is entering into the lumen. So wherever there is an active, wherever there is an active secretion of hydrogen ions, where is that happening? Where is this H plus ATPase present? It is present in the
DCT.
DCT and collecting tubular cells. Where whenever this H plus ATPase is actively secreting hydrogen ions, the hydrogen ion which is secreted, it is combining with the ammonium ion, the ammonia to form the ammonia. Already have ammonia. Ammonia combines with that H plus, and that is forming ammonium ion. So ammonium ion, once it is formed, it is trapped, because ammonium ion cannot cross the tubular membrane, and it combines non-covalently or passively with the chloride, and it is pushed. Okay. So this is another very important buffer system which is there in the kidneys. Ammonium ion buffer system. And whenever a buffer system is buffering hydrogen ions, you must remember, you saw that in the phosphate also. What is happening here in the basolateral membrane? Anybody can unmute themselves and tell me? You saw that in the phosphate buffer system also. Something you have to add before bicarbonate ion.
Bicarbonate exchanger.
There is no exchanger there. There is no exchanger there. Is it an exchanger? It is just one arrow, no? It is just one arrow. There is no exchanger here.
New bicarbonate.
Yeah, yes. New bicarbonate ion is formed. You have seen that in the previous one also, no? Whenever you have the phosphate buffer system and the hydrogen ions are being buffered by the phosphate buffer system, in the basolateral side you had a new bicarbonate ion formed. Right? So same thing you see in the ammonium ion buffer system. See, so hydrogen ion is being buffered by ammonia. It is trapped and converted into ammonium ion and trapped here. And on the basolateral side, you have the new bicarbonate. Okay, understood? So this is how the kidneys are playing a major role in the maintenance of acid-base balance. This is a very, 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 very frequently asked question. Okay, so you have to remember those diagrams. The sodium H plus exchanger, the H plus ATPase pump where it is present, and the buffer systems, the phosphate buffer system, and the ammonium ion buffer system, and how the filtered bicarbonate ions are absorbed, and how the filtered bicarbonate ions are reabsorbed, how the hydrogen ion is being secreted, I already told you, and then how the new bicarbonate ions are being. Okay, so any doubts till here you can ask. Please practice these diagrams. Please remember the common sense that one general statement: luminal membrane and basolateral membrane are having different transport proteins in different parts of the nephrons. You must read up about the transport mechanisms across the cell membrane if at all you want to make any sense of the tubular renal function. So understood here? Shall I move on? Anything you want me to repeat? Raise your hands if I can continue. Or you can unmute and ask me any doubts. At least 10 on each side should be raising their hands. Okay, so I'll move on. So this is an algorithm which will help you to understand simple acid-base disturbances. And please remember, I keep telling it's there even in the diagram there it is written footnote, simple acid-base disorders, and we all know that life is not simple. Okay, so you most often you'll get mixed acid-base disorders whenever you see in the hospital. But anyhow, as a first-year MBBS student, this algorithm will help you to understand some of the acid-base disorders. Okay, so whenever you get an arterial blood sample, very important, and you see the pH of that arterial sample. Okay, so the pH is less than 7.4 means there is acidosis. Okay, pH is less than 7.4, it is acidosis. So this acidosis, we have to find out whether it is a metabolic acidosis or a respiratory acidosis with the compensation from the lungs and kidneys. Okay, so acidosis is there, and the bicarbonate is less than 24 milliequivalents per liter, then it is a metabolic acidosis. And if you see the PCO2, the respiratory compensation for this will be decreased in the partial pressure of, it will be trying to blow off more of this thing there, okay, carbon dioxide. And then the PCO2 is more than 40 millimeters of mercury, then it is a respiratory acidosis. And then the renal compensation will be, the kidneys will be forming new bicarbonate ions and reabsorbing all the filtered bicarbonate ions. And then you'll have that, even though it is acidosis, the bicarbonate is more than 24 milliequivalents per liter. Okay. So when you go to the other side of this flow chart, to the other side of this flow chart, the reverse you will see. So if it is more than 7.4, it is alkalosis. And if the bicarbonate is more than 24 milliequivalents, it is metabolic alkalosis. But if the PCO2 is less than 40, it is respiratory alkalosis. In metabolic alkalosis, there will be a respiratory compensation. The lungs will start retaining carbon dioxide, and the PCO2 will be more than 40. And here this one. Whereas if it is a respiratory alkalosis where the PCO2 is less than 40 millimeters of mercury, the renal compensation will be, it will start removing bicarbonate, and bicarbonate will be. Then you have something called as an acid-base nomogram. Some people also call this a Sigurd-Andersen nomogram, which will help us to analyze more complicated acid-base abnormalities, where we draw a graph using, where we show the arterial plasma bicarbonate on the vertical axis, arterial blood pH on the lower horizontal axis, and the upper we take arterial blood hydrogen ion constant, and we look at PCO2 at different points. This is okay. So have you you please take down this flow chart. Please tell me once you have finished. You raise your hand. Once you have finished, you can. Office. Okay. Shall I continue? Shall I continue? At least 10 must raise
Yes.
this. Okay. So we have completed most of the topics you had asked me to revise, except maybe diuretics is there. Okay. So I have maybe less than a minute here. So what is a diuretic? A diuretic is a substance which is going to increase the urine volume output. Okay. Any substance which is going to cause an increase in the urine volume output is called as a diuretic. And the process of excreting a large volume of urine is called as diuresis. Any person who is excreting large volumes of urine, we say that he is having diuresis. And a substance which we use to make a person to excrete large volume of urine is called as a diuretic. Okay. Many diuretics are there depending on